Okay, now what are the factors affecting the regression rate? First of all, the pool diameter. Important thing is pool diameter D. Now, for petroleum fuels like petrol, diesel, tractor oil, can be said heavy diesel, then kerosene, which is in between diesel and petrol, based upon the densities, okay, volatilities, all are multi-component fuels. Okay. So, now people have done lot of experiments from very low diameter of 0.4 centimeter to 2300 centimeter. So, they varied the pool diameter in this range and got the regression rates, measured the regression rates, and they found that different regimes are in existence, different regimes. Basically, when you go for low diameters 0.4 centimeter to 5 centimeter, people have seen that the regression rate decreases as the pool diameter increase. Okay. In the low this. So, why it happens? When you see there is a surface area for the pool, say A. So, this is the diameter of the pool, say D. Okay. So, as T increases, A will increase. Generally, the mass burning rate also is expected to increase, because more fuel can evaporate from this area and participate in the flame. So, this is what is expected, correct. Now, what is, go back. So, now I can write R dot as m dot by A into rho L. Correct. So, now please see, when mass burning rate increases, area also increases, then the regression rate can decrease, because of the fact that the area increase can be more than the increase in the mass burning rate. Correct. So, that is the reason in this case the regression rate decreases as the pool diameter is increased. Okay, now go to the second regime, where the pool diameter is in the range of 5 centimeters to 12 centimeters. Okay. Regression rate remains almost constant. You can see this expression, when diameter increases, area increases, more vapor is available. See, in all these cases the flame is established over the entire area, correct. Mass burning rate happens only when the flame has spread over the entire area. So, now more area is captured by the flame, so more vapor will come out, but the mass burning rate need not increase linearly as the area. Please understand, that is the main problem here. So, the mass burning rate is expected to increase as the area increases, because more vapor will come out, the vaporization will increase, correct. Vaporization is surface phenomena. So, surface area increases, vaporization rate increases, but not exactly as the area increases or the diameter increases. So, we can say these three are true, D increases, A increases, M dot increases. But now, since R dot has this expression, I can say that the ratio of M dot by A dictates, rho L is constant for a given fuel. That is the important point here. So, in the second regime, the regression rate remains constant when the diameter or the surface area increases in this range, and the flames are phenomenally laminar in this range of this. So, obviously, when I say from 0.4 centimeter to about 12 centimeter, the laminar flames establish over the entire pool. This is the two regimes. In the first regime it decreases, second regime remains almost a constant. The third, when the pool diameter is increased above 12 centimeter, now there is a transition from laminar to turbulent regime. So, as observed by the fluctuations in the flame, correct. So, that is what. So, please understand that the transition is not so straightforward as we can calculate in a burner. So, I have a cylindrical burner in which a gaseous fuel is sent. So, based upon the exit velocity, so this is diameter of the burner d, etc., I can calculate Reynolds number, and I can say that if the Reynolds number is more than say 2300, etc., the case becomes transition from laminar to turbulent. But in the case of pool, yeah, diameter is increasing, mass loss rate also is increasing, but we cannot exactly calculate the Reynolds because the velocities of this, the induced velocity of the fuel vapor from the surface of the liquid to the gas phase, that may vary in a different way. Okay. So, but people have observed the flame oscillations, etc., and they have concluded that when the pool diameter is around say 12 centimeters, then the flame becomes a transitional flame where the characteristics of turbulent flame is also observed. Here what happens, the regression rate increases. In the first low diameter range of 0.4 to 5, there was a drop in the regression rate. Then further increase from 5 to 12, there was no change in the regression rate. Please understand that we are not talking about the mass loss rate here, we are talking about the regression rate. The regression rate basically is expressed as a function of mass loss rate as written below here. So, when transition occurs, the regression rate increases in which range? 12 centimeter to 1 meter. When the pool diameter is increased, we can see that the regression rate increases. So, again please see mass burning rate increases, but the area increase is not so much in this range of diameters. So, the regression rate also shows the same trend as that of the mass loss rate. Now, when the diameter of the pool is more than 1 meter, fully turbulent flame established over the pool, fully turbulent. Now, what happens? The regression rate again reaches the constant value. So, 2 times based upon diameter, the regression rate reaches the constant value. One in the laminar regime between the diameters of 5 centimeters to 12 centimeters, regression rate remains almost at a constant value. Similarly, when the diameter is increased beyond 1 meter, it goes to a constant value of 4 millimeters per minute. Do you understand? So, mass burning rate continuously can increase because of the area increase, but the regression rate has different regimes. So, these are the important points about the regression rates, which is affected by the pool diameter. Now, let us talk about some other features of the flame which is established over the liquid surface entirely. The average flame height, because flame is actually oscillating. The average flame height when it is normalized by the pan diameter. So, I say flame height, length of the flame divided by the pan diameter or the pool diameter, pan or pool you can say, pool diameter d decreases continuously. Okay, decreases continuously in both laminar and transition regimes and attains a constant value in the turbulent regime. This is another aspect. Okay. So, why it is so? This is because of several things. First one is the mass burning rate, and the mass burning rate will, when there is a phase change, there is a induced velocity perpendicular to the liquid surface, that will have some momentum contribution from the liquid surface. So, that is a convection, correct. That actually causes a entrainment of the air from the surroundings. So, when the mass burning rate increases, the air entrainment will also increase basically. That means more mixing can occur and the flame height will reduce. So, that is what is happening in both. The flame height reduces with respect to the, and also we are non-dimensionalizing with the pan diameter, which is also increasing. So, this quantity LF by D shows a decreasing trend with increasing pool diameter in all the regimes, like not all regimes, laminar and transition regimes, and it remains almost constant in the turbulent regime when the d is greater than 1 meter. This is one of the aspects. So, flame height. So, mass loss rate increases, regression rate has different regimes, and the average flame height also shows different regimes here. Now, as far as the heat transfer is concerned, conduction from the flame and walls also is, walls of the pan also will be heated. Here also flame anchors here, so this is also heated. So, this will also have some heat flux to the liquid. So, conduction from the flame as well as from the walls, that will be the predominant heat transfer mode apart from convection in smaller pools. That means the smaller pools, radiation need not be taken into account. It is very, very low. The radiation contribution is very, very low. This is one of the things. Then the flame standoff. So, what is flame standoff? Let us draw a pool and a flame forms over this surface like this. So, flame forms. So, now what is flame standoff? Taken any location on the pool surface, the average height at which the flame is established. So, this is called flame standoff XF, and this actually varies along the pool surface basically. It is, say for example, circular pool, it is very low of order of 1 mm or 2 mm at the edges, and it is increased and reaches the maximum value at the center of the pool XF, that is called flame standoff. The distance between the flame average flame location and the surface of the liquid fuel pool, that is the flame standoff, that dictates the conduction. Obviously, when the flame is very close to the pool surface, the conduction heat transfer will be very high. On the other hand, when the flame is so that means always the center, there are two aspects. The center, the flame heat feedback will be low. That means the pool actually is not uniformly heated by the flame. It is heated at a faster rate at the circumference, and towards the center it is poorly heated. Similarly, at the edges or the circumference of this pool, more air will be available. Central location, the air will be, the oxygen will not be there. So, it is oxygen starved at the center. These are the aspects of the pool flames. So, these are the factors contributing. The air entrainment, flame standoff variation, etc. contributes to the variation in the regression rate, average flame height, etc. So, in turbulent regime, we have seen two things. One is the flame standoff remains almost a constant, like LF by D. Regression rate also remains almost a constant in the previous slide. Regression rate also remains almost constant, the turbulent regime. Why? Because the turbulent mixing, correct, the flame oscillates a lot, turbulent mixing is very high. So, the irrespective of the diameter greater than 1 mm, 1 meter, you see that the flame standoff does not affect much, because it is actually oscillating. The average flame standoff remains same over the entire thing. So, we can see that the effect of the diameter does not play a role in the turbulent regime. As opposed to the gaseous fuel, we have shown that the flame height of the turbulent flame gaseous fuel depends on the diameter of the port or the burner. Okay. So, now formation of fuel rich vapor between the flame and the surface decreases the regression rate. As I told you, the center part is starved by the oxygen, that means the mixture is not there. Fuel rich vapor only is present at that point. So, if it is not removed quickly, then the regression rate will drop or the burning rate will drop. Okay, now, as the turbulence pitches in, higher rates of mixing, that's what we just told here, and the regression rates actually increases and becomes a constant after that, because of the fact that the see, when you increase the diameter, the flame standoff also can increase at the towards the center, but due to the oscillation, this is not going to come. So, the regression rate increase is not with respect to the diameter here, it is with respect to the laminar regime. When compared to the laminar regime and transition regime, regression rates, at the turbulent regime the regression rate will be higher. And when you increase the flame, when you increase the pool diameter more than 1 meter, the radiative heat transfer becomes a dominant thing here. Okay, radiative heat transfer becomes dominant. So such pools normally are very sooty, and soot radiation also contributes. So the radiative heat flux towards the surface also becomes very important. And the maximum value of regression rate which is asymptotically reached is also attained in this particular turbulent regime. So let us talk about asymptotic value of the regression rate R dot max, which is obtained in the pools having diameter larger than 1 meter. So a simple correlation of the maximum regression rate with respect to the heat of combustion calorific value and the net heat of vaporization is correlated like this. See, the heat released to the heat absorbed by the liquid, that ratio is used for correlating the maximum regression rate, where C1 is an empirical constant. So some value based upon the configuration and other things. So delta H is the heat of combustion, delta HV on the other hand is a sum of latent heat of vaporization and the sensible heat. Latent heat of vaporization is at the boiling point, and the sensible heat heats up the liquid from any temperature to the boiling point. As I told you, when this pool burning occurs, the surface or liquid temperature will not exceed the boiling point. It will be a couple of Kelvin lesser than the boiling point. So the net heat of vaporization includes the sensible heat as well as the latent heat, and this can be evaluated when you have CPL expressed as a polynomial of temperature like this. Then you can integrate this and find the sensible heat from T to T boil and add the latent heat, so that you get this expression. So now the correlation for the maximum regression rate, this is asymptotically reached. Do you understand? So when you talk about the maximum, we don't worry about the diameter of the pool anymore. That is the maximum. More than 1 meter maximum petroleum fuels, it has been shown clearly that the maximum regression rate is attained, and the correlation depends upon the heat released in the flame divided by the heat absorbed by the liquid fuel. Now similarly, we can, once I get the regression rate for the maximum condition, okay, asymptotic condition, the mass burning rate flux, that is mass burning rate per unit area m dot double dash, can also be calculated. M dot double dash maximum will be equal to the maximum regression rate into density of the fuel. That is another constant, that is all. Density of fuel goes as about 1000. So you can see that empirical constant reduces from increases from 10 power minus 6 to 10 power minus 3. So this is the asymptotic regression rate. Now people have given correlations for this, okay, to calculate. So now please understand, this is the maximum burning rate. Now I want, when the diameter is lesser than this, say for example lesser than 1 meter, can I somehow correlate the mass burning rate? Yes, we can do that. So a correlation was given by these two scientists in 1961, where the mass burning rate per unit area was correlated to the maximum mass loss. It is known for any fuel, it is dependent on fuel, into 1 minus exponent of minus kappa, beta and diameter d, that is pool diameter, that is all. Now, this kappa is called extinction coefficient, which has a unit of 1 by meter. Beta is the mean beam length correction, which does not have any unit. So, here for a given liquid fuel, kappa beta value is known, pool diameter is also known, asymptotic burning flux also is known. So, we can calculate the mass burning rate per unit area for any other diameter based upon the maximum mass burning rate. So, this is used. So, now this d is the pool diameter for circular pools, but it is hydraulic diameter for non-circular pools. So, for example, if it is a square pool or rectangular pool, etc., then you have to calculate d as 4 times area of cross section divided by the perimeter. So, that is the hydraulic diameter that will be used for this correlation. So, once you know that experiments have shown that when you go to turbulent regime, regression rate remains almost constant and maximum. This maximum regression rate is calculated as a function of heat of combustion and the latent heat. Now, this not latent heat, the heat of vaporization, which includes latent heat. Now, from this, using the definition of the mass burning rate, see, mass burning rate is actually the regression rate into area into rho L. So, mass burning rate flux will be equal to m dot by A, which will be equal to regression rate into rho L. So, using that I can find the maximum mass burning rate per unit area as a function of maximum regression rate. And I now correlation for the mass burning rate per unit area at any other diameter which is lesser than 1 meter can also be calculated using this. So, this is about the mass burning rate.
55 minutes.
Okay. So, now I will introduce some concepts which are important for theoretical analysis of steady mass burning rate. So, now please understand that let us take a pool of some length L and enough depth d. When I say enough depth, this depth is not going to affect the steadiness of the mass burning rate. Please understand that if the depth is too low, then the mass burning rate need not be steady. Or we can say that I supply the fuel at the rate at which this burns, so that the burning rate is steady. So, what is the steady burning rate of this configuration we can see. Now, moreover, what I can try to do here is I have some velocity of air, okay, say V air or U infinity something. A free stream is slow, free stream oxidation flow is taking place. So, that there is a boundary layer which is formed over the liquid. So, the boundary layer. So, this boundary layer is formed over the liquid surface. Now, what I have shown here is a small portion where there is a boundary layer. So, boundary layer at this particular position x. So, this is x equal to 0, this is x direction, this origin x equal to 0. So, at any x given x, I can say that boundary layer has a thickness here, thickness of del. So, I take a small portion. So, this is the given x at which the boundary layer has a thickness of del. So, now I say I will change the coordinates because I am actually having the x starting from in this direction. So, this is x for me and let us say this is y then I will say origin, the leading edge is y equal to 0 and here at a given y the boundary layer thickness is x equal to del. So, x is in the vertical direction. Okay. That is the nomenclature I have. Now, when you ignite this, fuel vapors come from the surface oxygen comes from the surroundings and a flame is actually formed like this. Again the flame will resemble a boundary layer type of flame, and at this particular location you can see there is a, in the same location of y, I will have a distance for the flame to stand off from the surface, which I call xf. So this is a scenario, there is a boundary layer, there is a flame formed in between the boundary layer thickness and the surface, that is the flame location at the particular x. This is actually particular y, this is the x direction. Okay, this is the given y location. From the leading edge y equal to 0, I am taking a particular y value at which I have a given value for del and given value for xf. Actually the value of del increases with the length as y increases. Similarly the flame standoff also increases as we move from the leading edge towards the trailing edge. This is the problem under consideration, and steadily it burns. Okay, now some aspect we will try to see. What happens? The fuel comes from the surface, feeds the flame. So the fuel mass fraction at the surface is YFS, and at the flame the fuel mass fraction YF equal to 0, that means fuel is consumed. Similarly, from the far field oxygen comes in, the oxygen mass fraction at the boundary of the boundary layer will be YO infinity. So this will be 0.232 for the normal air. Now here YO will be equal to 0. Why? Because at the flame surface the fuel is completely consumed, oxygen from the ambient also is completely consumed. That means there is no fuel available in this zone between the flame and the boundary layer. So this is called outer zone, and there is no oxygen available in this zone between the flame and the fuel surface. So this is the inner zone. So I have to have two solutions, one for the inner zone, one for the outer zone. Now what happens in the flame? The flame, a infinitely fast rate chemistry occurs. That means whenever the fuel from the surface and oxidizer from the ambient meets and mixes at stoichiometric proportions, immediately it is consumed, and the flame has 0 thickness. Okay, 0 thickness flame. Do you understand? So we are talking about a convection and a laminar regime. That is a flame. So this L basically is such that L is lesser than L critical. Okay. See, where for boundary layer, as the L increases, initially a laminar boundary layer forms, then transition to turbulence occur and turbulent boundary layer forms. Correct? So when you, in this case also, in the over the liquid pool, initially laminar boundary layer forms. So now I select the value of L such that it is less than the critical value for the transition to occur. Or I can say the Reynolds number calculated based upon L, which is nothing but rho of air U infinity L by mu. It is less than 5 into 10 power 5, which is critical Reynolds number for the transition from laminar to turbulent to occur. So what I am talking about here in the theoretical analysis is the laminar flame which is established over a liquid fuel pool, where the steady burning of the liquid fuel occurs. So at every point the flame is located at a given distance from the surface and it is steady. It is exactly located at that particular location. The surface does not regress, and surface does not regress at the faster rate because of the fact that it is slow burning. Okay, and the velocity, length, etc. are chosen such that the Reynolds number remains within the critical value for the transition from laminar to turbulence. So, this is the problem statement. And one more important assumption is I consider zero thickness flame where infinitely fast chemical reaction in the gas phase occurs. So, gas phase reaction is infinitely fast. So, these are the considerations here, and please understand that I am talking about the coordinate x, which is measured from the surface of the fuel. So, x equal to 0 here, and I go, and the boundary layer at any given, so y is the direction along the pool surface, and y equal to 0 at the leading edge of the pool. So, at any given y value, I have a certain thickness for the boundary layer, which is x equal to del. Similarly, there is a flame standoff at that particular y, which is x equal to xf. So, xf, and I am now interested in getting the solution for a particular location y to find the variation of temperature, yf, mass, flux, etc. in inner zone, and temperature, yo, etc. in the outer zone. Okay. I will stop here and continue about the theoretical analysis tomorrow.